All right, this is the last section of chapter 1. So that probably means that we have a test coming up. And we do. Do you know when? Next week. Which day?
Friday.
Wednesday. Levi's got it. It's Wednesday. We will do a test review on Monday, and we have the test on Wednesday. Okay? So we're going to finish section 1.5 today. We're looking at infinite limits. Okay, so if you don't have things printed out today, it's going to be far too much writing for you to get it all written down. Just a warning. So do the best you can and then fill it in later. Infinite limits. So we're going to let f be a function that's defined at every real number in an open interval, containing c except possibly at c itself. Okay, so if there's any holes or jumps or anything like that, it only happens at c. The statement, the limit as x approaches c of f of x will be infinity when we have m greater than 0, there is a delta greater than 0, such that f of x is greater than m whenever 0 is less than the absolute value of x minus c is less than delta. And a similar statement can be made for n that's negative. Now, I'm not asking you to memorize this one. We have one you memorized and or will be memorizing before the test that looks kind of like this, right? It does. This one's very similar, and let me talk to you in a picture form about what's happening so you can make sense of all the deltas and the epsilons and all the things that are going on in this description. So, let's see. So I need a graph. We're going to draw a graph like this. You can draw this in the space on your paper as well. It's going to have an asymptote the way we're going to draw it. We'll draw it in right here. And we're saying that this value right here where the asymptote is the c value. And we're going to have a graph that looks something like this. So far, so good? It's defined everywhere except at c. Right? Defined means it has a y value. It has a y value for that function everywhere except for at c. So what this is saying is that there's an m value that's greater than 0. It's the y value, an m value up here. It's greater than 0. And this happens whenever we get close enough. We'll draw here first. Close enough around m. We can come over here, go from here down to here. These are the values on m, that we are going to be down here also very close. That if you get really close on the one value, c, really close on the m value, they go together. That's exactly what we saw happen with our deltas and our epsilons before. If you get really, really close around one of them, you can get really, really close around the other one. And if you get any closer to c, then what happens is you get above m. Do you see that? There comes a point when if I'm closer to c than this little interval that I've marked, I'm going to be bigger than m on my y values. And we can do the same picture flipped upside down, and we can call m n. They're just arbitrary letters anyway. And there's a negative number down there that does the same thing. Right? So if it goes to negative infinity, we'd have the same picture flipped upside down. So one of the things I want you to be really careful of is that equal signs in this statement don't really mean that the limit exists. So when we write limit as x approaches c of f of x equals infinity, the limit's not existing. It still does not exist. But what this does is it tells us how it fails to exist. In particular, it's approaching something that's infinitely large. So the limit is not existing because there's a jump. In particular, the limit's not existing because there's an asymptote. So this is sort of telling you it doesn't exist, and this is the reason why. So it's unbounded as we get approaching c. As we approach c, the function is unbounded. All right, so in terms of what we're going to do when we do these, there's 3 different approaches we can take, 2 of them that are sort of the most natural or the most informative. One is a graph, and the other one's a table. So taking a look at this, it says determine whether f of x approaches infinity or negative infinity as x approaches 4 from the left or from the right. Now, if you just tried to put the number 4 in, what would happen? We get 0 in the denominator. It's not going to be defined. That's what's sort of red flagging us that we probably have an infinity or not a negative infinity showing up. And I don't have any way to reduce it with the numerator like we did back in 1-3, right? There's none of that going on. So we're going to consider this from a graphics perspective. If you have your calculator, feel free to pull that up. And we're caring about the value at 4. And there's going to be an asymptote there for the very reasons we've already stated. I get 0 in the denominator. But what we don't know is we don't know right now, just by giving the equation necessarily, what happens on the left-hand side and on the right-hand side of 4. In particular, for any general function, we could have it swooping up to infinity or swooping down to negative infinity, or one side doing one of each. All right, so we're going to put in the equation. We have negative 1 over, and my calculator makes me put parentheses in the denominator, x minus 4. And right now I probably have some random window set up from the last time we worked together, so I'm just going to make it into a regular standard window. So if you hit the zoom button, number 6 gets you a negative 10 to 10, negative 10 to 10 window, which for the purposes of what we're doing is probably going to be sufficient. So on our graph, and I'm going to transpose this over to our slide. It looks something like that. Agree? Okay, so from the left-hand side of the graph, as I get close to the value of 4, am I going towards negative infinity or towards positive infinity? Positive infinity. So up here, this one's positive infinity. So the limit as x approaches 4 from the left of f of x, we would say it doesn't exist, but it's going towards infinity. And then what happens if I move from the right-hand side toward 4? Yeah, it's negative infinity on that one, right? It's actually going unbounded in a negative direction down here. So we would say the limit as x approaches 4 from the right of f of x is negative infinity. You have to draw the picture to justify that, okay? So you sketch the image that your graph's giving you, and you justify it with a graph. That's one option. Does that make sense? So you're interpreting it from a graphical perspective. So let's talk a little bit more about those vertical asymptotes we've mentioned. So as f of x approaches infinity or negative infinity from the left to the right, then this line, x equals c, is called a vertical asymptote of the graph. You've seen vertical asymptotes before. They usually come about for the first time in an Algebra 2 class in high school. Yours may have had a different name for it, but we definitely see them there. We see them again in pre-calculus or college algebra as well. So you've seen vertical asymptotes before. So a vertical asymptote is a line, typically speaking, that you get close to vertically and you don't touch. A little bit more about vertical asymptotes. If we have a rational function, so if f and g are continuous, they're not, f of c is not 0, and g of c is, then there will exist an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval. All the conditions are met, okay? Then the graph of the function h of x equals f of x over g of x has a vertical asymptote x equals c. Okay, all this is saying is that the denominator equals 0 and the numerator doesn't. And when that happens, we're going to get a vertical asymptote. And we saw that happen back in 1-3 already, right? In particular, we were looking for the opposite. We were looking for them both to be 0 and able to factor and cancel something, right? And then when it didn't, we had to say does not exist, but we didn't really go any further into what happens next. And then in 1.4, we talked about continuity. Can we cancel them out and make it a removable discontinuity? Or is it still there and now it's non-removable, right? So our vertical asymptotes are creating that non-removable discontinuity we talked about in 1.4. So when we're simply asked to find vertical asymptotes, we have to be a little bit careful. It is true that vertical asymptotes are the locations where the denominator is 0, but that's not always what happens. Some of the ones that we saw happen back in 1.3 and then again in 1.4 had the numerator and the denominator canceling some pieces, right? And when they canceled, they didn't create vertical asymptotes. Do you remember what we said they created? Holes. So when we're asked to find a vertical asymptote, we can't just look at the denominator and ignore the numerator. There's a relationship between the two of them, and depending on what happens will depend on what type of a discontinuity we have. So when we're doing this, we are in fact going to factor both pieces. Let's start with the top. How does this numerator factor? X plus 3 and x minus 3. We've mentioned this before, but that's a difference of squares. The x value is squared, and then 3 squared is 9, so the second value is also a squared number, so it can be factored as x plus 3, x minus 3. We also talked about that in terms of conjugates. X plus 3 and x minus 3 are conjugates of one another. That's why they don't have that middle x term, linear term. How about the denominator? X, what was it? Okay. So one of the rules of thumb to kind of keep in mind as you're working with this is that our expectation doesn't mean it's always going to be met. Expectations are not always met, right? But our expectation is that there's going to be something probably in common in terms of factors from top to bottom, right? That's more the norm than the exception. So if you're having trouble factoring something, keep in mind, is there anything from the top that's going to show back up on bottom? And there usually is. And in fact, what shows up here? Yeah, the x minus 3. So the fact that I can cancel those means that they did not create, that value of the x minus 3 did not create a vertical asymptote, it created a hole. So the only problem right here is this piece. So how can I use x plus 1 and find the corresponding vertical asymptote? It's negative 1. So it's the value that would make that equal to 0. If it's something that's more complicated and you wanted to actually set it equal to 0, you could do that too. This one was pretty easy to see, but if you don't see it, this is what you do. You just set it equal to 0 and solve. Our vertical asymptote here is x equal negative 1. Now, while you have to show the work that we just showed, how could you confirm that this is correct? A graph. Yeah. You have a calculator. Use it, right? Graph it. Make sure that it looks like, visually speaking, that sure enough there's that swooping up or down behavior, either both going up, both going down, or splitting, doesn't matter. But it looks like that there is this sort of a unbounded behavior happening, around negative 1-ish. And if you find when you do that, it doesn't look like it's at negative 1, then one of two things happen. You either put it in your calculator wrong, which is always a possibility, right? Let's be real. We typo things all the time. Or maybe you made a sign error. Or maybe you canceled the wrong thing by mistake. So it gives you pause to go back and to check your work, one way or another. Check the work you put into the calculator or check the work that you did on the paper, okay? All right, next one. It says to determine whether the graph of the function has a vertical asymptote or a removable discontinuity at x equal negative 1. That phrase, removable discontinuity, what does that mean? It means hole. How do we decide if we have a hole or an asymptote? We look for factoring to see if things cancel. So, thinking about those things, looking at this function, what do you see? If I try to factor the numerator, Jackson's right. I'll get an imaginary number. Or you can simply say, I won't get something in the real numbers. It doesn't factor over the real numbers. You might be looking at that and saying, wait a minute, that looks kind of like this last one, x squared minus 9. What's the key difference between x squared minus 9 and the x squared plus 1? The sign. The sign. That's the big one, right? This is a difference of squares. factoring. I can do that. Even if the 9 weren't a nice number, let's say it were 5. Okay, well, we can do x minus the square root of 5 and x plus the square root of 5. It's factorable, right? But when I have a positive, right, addition happening between them, it's a sum of squares. I can't factor it, at least not over the real numbers. And all the calculus that we're going to be doing in Calc 1 through Calc 4, for those of you who might be taking a little bit more than just this class, is always in the real numbers. It's never over the imaginaries. Yeah, some of you are like, score. Definitely want to avoid those guys, okay? Well, yeah, it's not. So since I can't factor the numerator, which means I can't cancel out the denominator, what does that tell me? There's no holes. What else? There's a vertical asymptote. Those are the two choices, right? So we're going to write that down. So there is a vertical asymptote at x equal -1 because x squared plus 1 will not factor and reduce with x plus 1, sorry. Now, just because this one didn't factor at all, could we have something that factors on top and still doesn't reduce with the denominator? Yeah. If we had had that same numerator we had on the last problem, x squared minus 9 with x plus 1 as the denominator, it could factor in the numerator, but it still wouldn't reduce with the denominator, right? So I'd still have a vertical asymptote at x equal 1, even though the top factored. So it isn't about the top not factoring. It's about the fact that the top doesn't factor in a way that reduces with the denominator. Does that make sense? Okay. All right, a little bit more. So these are some properties of infinite limits. And once again, you may be looking at them and saying, Dr. Hands, didn't we already write these down? We did, but we didn't do them for infinite limits, right? We did them for finite limits. But the beauty of it is they're pretty much the same. So that's good news. C and L are real numbers, F and G are functions. The limit of f of x is infinity, and the limit of g of x is L. So when we take the sum or the difference, right, we add and subtract. This is basically infinity plus or minus L. So if you take infinity, something that's infinitely large, and you add or subtract something finite, it stays infinitely large, right? Yeah, absolutely. Same thing on the next one. You take something that's infinite and you multiply it by something that's finite. Well, if I have something infinite and I have something finite and I multiply them, it's still infinite. And in some ways you might think, and it even got bigger, right? Maybe. I mean, you know, it depends on what L is, but it's definitely still infinite. Infinity times something is still infinity. And on this one down here, we now have a constant on top, L, and we have something infinite on bottom. When you divide a number by something that gets infinitely large, the fraction gets infinitely small. So, infinitely small tending towards 0. Right, imagine, take a number, we'll just take the number 10. So if you do 1 divided by 10, and then 1 divided by 10 squared, and then 1 divided by 10 cubed, the denominator keeps getting bigger and bigger and bigger. That 1 divided by portion, all of that together, it gets infinitely small, tending towards 0. Similar properties will hold for the one-sided limits for these functions, and also for what happens if the L value becomes negative or positive. I get changes whether maybe you have negative infinity, right? So if we're working on what happens here, then we have to be a little bit more careful with that. But not in the sense that it doesn't still become infinite, right, or unbounded. All right, we have one last example for today. There it is. Okay, so I showed you how to find the one-sided limits. The question didn't word it quite like that. It asked it over here. It said no, that wasn't it. It was further back. There it was. It said find the one-sided limits, but it didn't say it that way. It said find out what happens as you approach 4 from the left and from the right. And that's the same question as what are the one-sided limits, which is how we answered it, right? And we did it with a graph. So one way to find one-sided limits is to do it with a graph. Another way to do that is with a table. So I'm going to show you a table on this one, then we'll check the graph just to make sure that it coincides and we agree with it. So this one wants us to find the one-sided limit as x approaches 2 from the what?
Left side.
From the left side. Okay, so if this is telling you it's approaching from the left, that means you can't be looking from the right. I know that sounds really obvious, but I ask this kind of a question on tests or quizzes sometimes, and I have people look from both directions. We're not supposed to be looking from both directions. This is a one-sided limit. It's only from the left. So if we're approaching this from the perspective of a one-sided limit, we need to use values that are bigger than 2 or smaller than 2? Smaller than 2. We've done this before. What are some numbers that are smaller than 2 that would be convenient to do for this? 1.9. 1.99 and 1.999. It's 1.2 all over again, right? Section 1.2 is what we did. Okay, so let's go to our calculator. So we have x squared over x squared minus 4. That's my equation. And I do not care about the graph right now. We'll come back to look at the graph, but we're looking at the table. So the table's under here. Again, if you've got a calculator you haven't used before, table setup means you go second window. It should say ask on the first line and auto on the second line. Ask and auto. That's how it's always going to work for the problems we're going to do. Okay, ask, auto. To go into the table, we hit second graph, and it takes us to the table. A bunch of values from last time and delete. And we're going to put the numbers in that we just wrote down. 1.9, 1.99, and 1.999. Okay? And we're going to arrow over on top of those values so that we write down how many decimals? 6. Good guess. 6 decimals. We're going to write down 6 decimals. So I've got negative 9.256410. And then, if I arrow down, I've got negative 99.250627. One further, I've got negative 0063. All right. These are my function values. What is happening as I go down this table? Infinitely negative, or negative infinity, right? So this limit should say negative infinity. There's another one-sided limit, but we weren't asked about it, right? We're not, so we don't care. It doesn't matter. Let's look at the graph for this too, because we've already got the screen to be able to do so. So I don't know why the screen is so dark right now. Oh, you know what? Nope, that's not it. Sorry, wrong button. That's not any better. Okay, anyway, let me get it close enough that I can point to it. So this is negative 2, and over here is positive 2. There's 2 asymptotes that I'm seeing, right? And that should make sense. If you were to take the denominator and you were to factor it, it factors into x plus 2 and x minus 2. Are we caring about 2 or negative 2? 2. But we're caring about 2 from the left side, okay? So this is 2, and this is the left side of 2. So as we do that, we're approaching negative infinity right here. See it? Okay, so I'm going to draw that on a screen as well so that it shows up on the video later. So our whole picture looks something like, nope, that's not right. Something like this-ish. And if we're counting or sort of observing carefully, it looks to be that these are our asymptotes here and here, and that they're at 2 and -2. The one we care about and the portion of the graph that we care about is right here. So if we were asked this question in an assignment and we were asked to justify it with a graph, we would identify using some kind of a circling, highlighting something that this is the part of the graph we're looking at to make that call. Does that make sense? Because I want to know that you're looking at the right part of the graph, because you could be looking and making the right decision but on the wrong part of the graph. Well, you should get some credit for the fact that you know what you're doing. You're just in the wrong spot. You know what I'm saying? Okay? So over here is where this graph is looking. Any questions? All right. Tanner? Yeah.
So we talked about like different ways of deciding, or like showing we can find it.
Yeah.
On like the quiz or homework, are you going to tell us which you prefer?
I'll either tell you or you can choose your own, and either one's right. In which case my answer key gives both choices. And I've done both before. Yeah, so it could go either direction. So no both, because you could be asked for either one, but then when you get there, you can use whatever you'd like if you're not told.